Now, let's start proving some of the beautiful properties of the Sturm-Liouville problems now that we've got this concept of self-adjoint operators L. So recall that the basic Sturm-Liouville problem is to find eigenfunctions v and eigenvalues lambda that satisfy Lv plus lambda r of x v is 0 for self-adjoint L. Now the first property we're going to prove is that eigenfunctions corresponding to distinct eigenvalues are orthogonal. And we'll then use that in some of the other proofs. Okay, so distinct eigenvalues mean that suppose there are two eigenvalues which are not equal to each other, lambda n and lambda n, and let's consider their corresponding non-zero eigenfunctions, Vn and Vn. Well, they satisfy this differential equation. So let's write that out. Lvn plus lambda n r Vn has to be 0, and Lvm plus lambda n r Vn has to be 0. Both of those are true. Now, multiply the first by Vm, multiply the second by Vn, subtract the two, and what do we get? So we get Vm into Lvn plus lambda n r Vn minus Vn into Lvm plus lambda n r Vm, and then has to be equal to the corresponding right hand side, which is 0 minus 0. Now, integrate this over the domain. So go integral from a to b of this expression, and let's expand these brackets. So it's Vm Lvn plus lambda n Vm r Vn minus Vn Lvm minus Vn lambda n r Vm dx has to be the integral of 0 over the domain, which is 0. Now look inside this integral, what have we got? We've got in those two terms something that relates to this concept of self-adjointness. So let's group them. It is the integral from a to b, Vn Lvn minus Vn Lvn dx. Then group those two terms and say plus the integral from a to b, lambda n Vm r Vn minus Vn lambda n r Vm dx, and all of that has to be 0. And if you notice the misprint, that lambda there, that's an r. Okay, now these two integrals, this first one is 0 as L is self-adjoint. Consequently, we have this integral has to be 0. Now, if you look at this integral, you see it's got a common component there. It's just the eigenvalues that are different. So this integral is the integral from a to b of lambda n minus lambda n of Vn Vm r dx. And in this, lambda n minus lambda n is a constant, so bring it outside the integral. Integral a to b Vn Vm r dx has to be, and all of that has to be 0. Now have a look at this product. we know that lambda n is not equal to lambda n, so this is non-zero. So something non-zero times this integral is 0 means this integral is 0. And that means that the eigenfunctions are orthogonal with weight function r as claimed. That's our first property. The second one is, for these Sturm-Liouville problems, the eigenvalues are always real, which is great because we don't have to bother about looking for complex ones. Okay, we prove this with contradiction. So, let's contradict by saying assume there exists an eigenvalue that is not real. In other words, it's got an imaginary component. Right. So, for example, it means its complex conjugate lambda bar is not equal to lambda, where we're going to use bars for complex conjugation. Okay, it's an eigenvalue, so there is a corresponding eigenfunction. V of x satisfying Lv plus lambda rv is equal to 0. And in general, if lambda is complex, the eigenfunction v will also be complex. And that eigenfunction is not 0, which we'll come back to at the end. Now let's have a look at a consequence of this. Let's take the complex conjugate of this equation. Okay, complex conjugate. And what happens? So a complex conjugate of a sum is the sum of complex conjugates. And 0 is its own complex conjugate. Then the complex conjugate of a product is the product of the complex conjugates. So we can write formally this, L bar operating V bar plus lambda bar R bar V bar is equal to 0. But now recollect in the Sturm-Liouville problems, we required L be real, in that the functions P of x were real, Q of x was real, and also d by dx is real. So that means the complex conjugate of L is itself L. So this term is just Lv bar. The eigenvalue is lambda bar. R is also real. It's one of the specifications, so R bar is R. So we know that equation is satisfied. What does that tell us? Well, it tells us that V bar is an eigenfunction corresponding to eigenvalue lambda bar. Yeah. And now, lambda bar, this thing that we now know is an eigenvalue, is not equal to lambda, which is also an eigenvalue. So let's apply this property. Since the two eigenvalues are not equal to each other, their corresponding eigenfunctions have to be orthogonal with weight function r. So we can immediately deduce that the integral from a to b of v bar times r dx has to be 0. But this product v bar, we know what that is. That is nothing other than mod v squared r dx, and that has to be 0. Okay, now remember that the weight function r, not only real, we required it to be positive, so that's always bigger than 0. And also v, the eigenfunction, cannot be 0 everywhere. It has to be non-zero for over some range of the domain, typically most of the range. So mod v squared is going to be bigger, typically is going to be bigger than 0 as well. It can only be 0 at isolated points. So this integrand is bigger than 0, and so this integral, this whole integral itself has to be bigger than 0. But that contradicts the fact that it's equal to 0. And that contradiction implies that the assumption is wrong, and the assumption is that lambda is not real. That's wrong, so the eigenvalues have to be real. That's it.